Hi all and welcome back. It's Gio with class number 15 of the course Signals and Systems 2 at UPF in Barcelona. For any questions on this class or any of the previous ones, feel free to get in touch via email or check my webpage for more information. In the last class, we learned details and properties of the region of convergence of the Laplace transform. We also introduced the formula for calculating the Laplace anti-transform, but we also saw that in many cases we can use simpler methods to calculate the anti-transform rather than employing the formula. Today we will continue by giving some important properties of the Laplace transform. So let's get started. The first property, as usual, is the simple linearity property or the property of superposition. So it's simply stated as follows. If you have a signal x1 with Laplace transform capital X1 and region of convergence R1, and you also have another signal x2 which has Laplace transform capital X2 and region of convergence R2, then a linear combination of them, ax1 plus bx2, will have as a Laplace transform the linear combination of the respective Laplace transforms. So that is ax1 of s plus bx2 of s. And the region of convergence will contain the intersection between the two regions of convergence, R1 intersection R2. However, it could also be larger than such intersection. So note that such regional convergence can be larger if a pole zero cancellation occurs when we perform the linear combination. We'll see some example. So here's an example. Let's take x of t as x1 of t minus x2 of t, where x1 has a Laplace transform x1 of s equal to 1 over s plus 1 with region of convergence, real part of s larger than minus 1. And let's assume that x2 of s, the Laplace transform of the signal x2 of t, is 1 over s plus 1 times s plus 2 with region of convergence, real part of s larger than minus 1. So what happens when we do the linear combination? You see this in the middle of the slide. So if we just do some simple algebraic calculations of x1 of s minus x2 of s, we see that in the end the fraction simplifies. We end up with s plus 1 over s plus 1 times s plus 2, so there's a pole zero cancellation. The pole in minus 1 cancels the 0 in minus 1 or vice versa. We end up with 1 over s plus 2, and the region of convergence in this case is real part of s larger than minus 2. So the region of convergence has extended. We can see the same thing graphically by looking at the bottom of the slide. So on the left we have the region of convergence of x1 of s. x1 of s, again it's written at the top, has only one pole in minus 1, and its region of convergence is a right half plane. Then in the middle we have the region of convergence of x2 of s. x2 of s has two poles in minus 1 and minus 2, and its region of convergence is to the right of the pole in minus 1. It's a right half plane. However, in x of s, which is represented at the bottom right, because of the cancellation of the pole in minus 1, there's only one pole left in minus 2. And for this reason, the region of convergence is real part of s larger than minus 2. So it is not simply the intersection of those two, but it is actually larger. Another simple property, yet useful, is the one of time shifting. This is similar to what we saw for the Fourier transform. So if x of t has Laplace transform x of s with region of convergence R, then simply a delay in x, or a time shift or anticipation, so x of t minus t0 will have as a Laplace transform the same x of s multiplied by e to minus s t0, so multiplied by that exponential. The region of convergence would not change in this case. Slightly different is the case of the shifting in the s domain. So this is similar to the shifting in the frequency domain for the Fourier transform. So again, for the same pair of Laplace transforms, if you have a shift in the S domain. So if from x of s you create x of s minus s0, where s0 is a complex number, then the corresponding anti-transform will be x of t multiplied by e to s0t. However, in this case, the region of convergence changes, and the new region of convergence will be r plus real part of s0. So basically the region of convergence, which is always a vertical strip somehow, will be shifted horizontally along the real axis by a quantity real part of s0. Well, that is normal because we have done a shift in the S domain. So all the poles and zeros that were, for example, at s equal a will now be moved to s equal a plus s0. That's why the shift, which you also see represented graphically at the bottom of the slide. So you have the original region of convergence on the left, R, and this is shifted on the right when you depict R1. What happens with time scaling? So if you create a signal x of at with a scaling a, then its Laplace transform will be 1 over magnitude of a x of s over a. So this is again similar to what happens to the Fourier transform. What about the region of convergence? It is also scaled. So the new region of convergence will be AR. So depending on the value of A, this can yield several effects. So when A is between 0 and 1, there's a compression of the region. When A is larger than 1, there is an expansion. And when A is negative, the region also is reversed. So it's mirrored with respect to the imaginary axis and also scaled depending on the value of A. And also we have that x of minus t, for example. So if we just do a time reversal of the signal, corresponds to x of minus s. So there's a reversal in the S domain. And the region of convergence in this case will be minus r. So it would be mirrored across the imaginary axis. Let's keep going with these basic properties. Conjugation. If you have the conjugate of signal, x conjugate of t, then its Laplace transform will be x conjugate of s conjugate with the same region of convergence. This is the equivalent of what we saw for the Fourier transform, if you recall. And in particular, when x is real, then we have the property that x of s is equal to s conjugate of s conjugate. So we have a sort of a symmetry. Very important is the convolution property. So if we have two signals, the same as before, x1 and x2 with Laplace transforms x1 of s and x2 of s and regions of convergence r1 and r2, and then we do the convolution of these two signals, then the Laplace transform will be the product of their Laplace transforms. So this is similar again to what happens with Fourier. It could be proven in a very similar way. And what about the new region of convergence? It will contain the intersection between R1 and R2, but it could also be larger if a zero pole cancellation occurs, for example. We have an example at the bottom of the slide. So take x1 and x2. In this particular case, they're one the reciprocal of the other. They have two different regions of convergence, obviously, because one has a pole in -2 and the other has a pole in -1. But when we multiply them, which is equivalent to doing the convolution of their respective anti-transforms, well, the product yields 1 because there's a simplification of two zeros with two poles. And of course, a function 1 always converges, and therefore the region of convergence is the whole plane S. So there has been a zero pole cancellation, and the new region of convergence does include the intersection between R1 and R2, but in this case is actually larger. Let's move on to differentiation. So if we do differentiation in the time domain, then the derivative of x of t in dt will have as a Laplace transform s times x of s. So differentiation corresponds to a multiplication by the complex variable s. Again, this is similar to what happens with the Fourier transform, where a differentiation in time corresponds to a product by j omega in frequency. And the new region of convergence will contain the original one, but it could be larger. The reason being that since we are now multiplying by s, if in the original region of convergence there were a pole of single multiplicity in the origin for s equals 0, this will be cancelled, and therefore the region of convergence will be extended. But in general, we can say that it contains it contains r. As an example, we take x of t equal u of t. This is at the bottom of the slide. Its derivative is the delta, the ideal impulse. So they respectively will have Laplace transforms 1 over s for the step u of t and 1 for delta of t. So you see that the original region of convergence, the one for the step, the one for 1 over s, was real part of s larger than 0, but the Laplace transform of the delta is 1 and it converges everywhere. So the region of convergence has been extended. And what about differentiating in the S domain? This is also very interesting and can be very useful also in our calculations. So if we have the derivative of x of s in the S, then the anti-transform of such function would be minus t x of t, where x of t was the original anti-transform of x of s. The region of convergence doesn't change. Now, the interesting fact about this is that it can be reapplied iteratively, and it can give us information about derivatives of a generic order of a certain function x of s. And this is particularly useful when we're operating with fractions of polynomials. So let's see examples. So we already know that if we have 1 over s plus a, and in particular with a region of convergence, real part of s larger than minus a, so in this case with a right half plane, then the anti-transform of that is e to minus at u of t. We have encountered this many times by now in our examples. But what about the second order? What about if we had a second order term at the denominator of such fraction? Well, that's when the S-domain differentiation rule comes handy, because we notice that minus the derivative of such 1 over s plus a is equal to 1 over s plus a squared. And therefore, because of the rule we have introduced in this slide, its anti-transform will be t e to minus at u of t, because of the rule of the multiplication by minus t. So just to clarify, we know that the term 1 over s plus a squared can be written as the derivative of 1 over s plus a times a sine minus 1. And we know that because it is the derivative of something, its anti-transform would be minus t, the anti-transform of that something. And this is how we come up with the second of the lines at the bottom of this slide, which says that t e minus at u of t corresponds to 1 over s plus a squared. So from now on, when we have to anti-transform a term of the second order, like 1 over s plus something squared, we know that the anti-transform basically has a term t, which is introduced, that multiplies the exponential. The same thing can be repeated as I anticipated, and therefore we can come up with transform pairs for terms of third order, or even in general the nth order. So for the third order, you see it on this slide, by iterating the procedure, we get that t squared over 2 e minus at u of t corresponds to 1 over s plus a cubed, and so on and so forth. So here we have an example of what I just said. So let's look at the top of the slide. We have x of s, for example, given by 2s squared plus 5s plus 5 over s plus 1 squared times s plus 2. So if we want to anti-transform such fractional polynomials, we use partial fraction expansions first. So we know that because this fraction has a term of the second order, we will need, for that term, we will need two fractional expansions, one of the first and one of the second order. This is really critical. So in the end, we will need three, because we will need one term for s plus 1 squared, one term for s plus 1, and one term for s plus 2. Each one will have its own coefficient, and if we solve the equation, we can determine the three coefficients, and in this case they would be 2 minus 1 and plus 3. Therefore we can write x of s as it is written at the top of the slide as 2 over s plus 1 squared minus 1 over s plus 1 plus 3 over s plus 2. In this case, we are assuming that the region of convergence is real part of s larger than minus 1. It is given to us. So now we are in a position to anti-transform. Because the region of convergence is a right half plane, then each of the three anti-transforms will have to be a right-sided signal. And we also know how to anti-transform the term of the second order, because we have just seen it. It's actually at the bottom of this slide. So in the end, we have that x of t will be given by 2 t e to minus t u of t minus e to minus t u of t plus 3 e to minus 2t u of t. What about time domain integration? Well, in the case of integration, the integral function of x of t, which can be written as the integral between minus infinity and t of x of tau d tau, where tau is a mute variable, will have as a Laplace transform the original x of s divided by s. So 1 over s, x of s. And the region of convergence, because of such division by s, which introduces or might introduce a pole in s equals 0, will contain r intersection real part of s larger than 0. Now we will conclude with two very interesting theorems that apply to the Laplace transform. The first theorem is called the initial value theorem. So it states that if x of t signal is 0 for any negative time, so it's causal, and if x of t also has no impulses or any higher order singularities at t equals 0, so nothing strange, then the value of x in 0 on the right, meaning x of 0 plus, so the limit of x of t as we approach 0 from positive times, can be actually calculated by looking at its Laplace transform. And how? It is given by the limit for s that goes to infinity of s times x of s. So this is why it's called the initial value theorem, because we can calculate the initial value of x just by looking at its Laplace transform, multiplying it by s and taking that limit. There's also corresponding final value theorem. So for the similar conditions, so if x of t is 0 for negative times, meaning it's causal, and if x of t has a finite limit as t goes to infinity, so if x of t doesn't diverge for infinite time, then we can calculate the final value of t, which is the limit of x of t for t that goes to infinity, by looking at its Laplace transform once again, multiplying it by s and taking the limit for s that goes to 0 in this case. So it's quite interesting. Here we have an example for the initial value theorem. So let's assume that our signal is x of t equal e to minus 2t u of t plus e to minus t cosine of 3t u of t. We can calculate the Laplace transform of such signal. We are able to do this already. How to do that? Well, we know the Laplace transform of the first term, e to minus t u of t. Regarding the second term, it's a cosine, so we are able to write it as a sum of two different functions by writing the cosine as a sum of two complex exponentials. And therefore, we can calculate the Laplace transforms easily of each of the three terms. Then we can put them together into a single fraction, and we obtain what's written in the slide. X of s equal 2s squared plus 5s plus 12 over s squared plus 2s plus 10 times s plus 2. Right, so let's test the initial value theorem in this case. If we look at the time domain, then the limit of x of t as t approaches 0 from positive times can be easily found. E to minus 2t u of t would converge to 1, and e to minus t cosine 3t u of t will also converge to 1 for t that goes to 0 from the right. Notice that going to 0 from the right is very important, because the function u of t is 1 from the right, but it will be 0 from the left because it's discontinuous. So we know that the initial value is 2. And now we're asking, could we find this just by looking at the Laplace transform? Yes, we could. As a matter of fact, if we do as the theorem says, if we take the limit for s that goes to infinity of s x of s, we have the limit of that fraction represented there, which is simply x of s multiplied by s. And we see that for s that goes to infinity, we just have to look at the terms of the highest order, which are the terms in s cubed, and we see that the limit is simply 2. So everything makes sense. Right, so today we'll learn some more important properties of the Laplace transform. We will make use of some of them in the next class, where we will characterize linear and time invariant systems through the Laplace transform. See you in the next class.